So I know that last time our online meeting might have been a bit of a headache for you, and but I'm very glad to say that today's lecture will continue to be a really bad headache for you. However, where we're aiming to get by the end of the lecture today, which we should be able to get to, is a result where you can say, oh, wait a minute, I know what we do, and then we work with it, okay? But I've got a little bit more wading through the mathematical details before we break onto this sort of replay of the past, is what I might call it. So let me make some comments, some about what we talked about last time, and then we're going to dive back into some of the meat of what we talked about, or what we're going to talk about today. So recall, if we have a manifold, which, you know, I draw with these curvy sides just so that you don't think this manifold is a copy of flat Euclidean space Rn, because it's not. Okay, if I have a manifold M, then one of the definitions of this manifold is an atlas of charts, or actually a maximal atlas of charts, and each chart comes with a map phi alpha, which is a map into a copy of Rn. And the image of the map is open in Rn, and there's a lot of details that we talked about last time. And then we talked about how if we have the overlap of two charts, then we have essentially the map. And so if I call this chart U beta, just to give it a name, we can consider a map from this Euclidean space to this Euclidean space, which uses the inverse of this map and then this map. And then if that function is differentially continuous, or it's CP differentially continuous, then these transition functions establish that our manifold has this differentiable continuity. However, you know, an important observation is to realize that, and I think I might have ended last time with this, but I'll repeat it. You might think that according to this description, only this much of the manifold has to be differentiably continuous. Okay? Because this is the only part that's on an overlap. Now remember, you have to cover the entire manifold by charts. So, you know, we might have, to fill it up, we might have something like this. And this is why I say it's really hard to draw atlases, because they get really busy really quick. But notice we've only got a handful of overlaps. And on those overlaps, we can show that it's differentiable, but there's regions of the space where it's obviously not required to be differentiable, right? Right?
No, because you can have an infinite number of atlases that all overlap on every part of the...
Exactly. The thing is you have to remember that the manifold is not defined by a single atlas. It's defined by the maximal atlas. That is, it takes all atlases and it sort of identifies them all as a maximal atlas. But basically it means whatever properties you expect to hold for one atlas have to hold for another atlas. Okay? So I can easily take these patches and shift them around to cover all of the regions which are not part of an overlap in this particular atlas. I can take everything and shift it to the right a little bit. And you know, and then this thing will move a little bit to the right, and this will move a little bit to the right. Do you see what I'm saying? So the fact that every single atlas has to satisfy this means we can cover the entire manifold with these overlaps. Okay? Well, if we're really lucky, if a manifold can be covered by a single chart, okay, so if we have, for example, as you'll prove in your homework, an infinite cylinder, okay, we can cover this with a single chart. And so that might lead you to ask, well, if you can cover it with a single chart, there's no overlap, because you don't have two charts which overlap, much less 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10, but is this thing differentiable? Why?
You can also cover it with two charts.
Exactly, because you can cover it with two charts. Just because you can only cover it with one chart doesn't mean you can't use 2 or 3 or 4 or infinity. Okay? Now, in terms of charts which cover the entire manifold, say I take a chart, I call it U1, and then associated with this chart, I have a map into Rn, which remember, in Rn we can set up a coordinate system. Okay, because in Rn the normal coordinate definitions work. Okay? And then we can consider, instead of the chart U1, and I'm just using the simple example of a manifold which can be completely covered by one chart, we could instead consider covering the entire manifold by a different chart, U2, okay? Where U2 might have a map into Rn, and I don't know why I'm being stupid. I've got it written in my notes in a special way, but so in reality, what that arrow in this picture meant was added to this picture. I just couldn't interpret my notes. Anyway, so we can add in a second chart, U2, which also covers the manifold. So these two charts are just sitting on top of each other. We could take either one of them to define an atlas, or we could take both of them to define an atlas. Okay? But if we do that, here's the nice difference. They're both maps into Rn, where remember, n is the dimensionality of the manifold. So the chart always maps from an n-dimensional space into an n-dimensional space, n-dimensional space into an n-dimensional space. Watch this. However, in this system, maybe we use that as our coordinates. Okay? What am I doing? What am I doing with these two charts which are overlapping, and this uses these coordinates and these use these coordinates?
Rotating,
Say it again?
rotating the coordinates.
Exactly, I'm just doing a coordinate change. That's all I'm doing. Okay? So coordinate changes are part of this story of chart mappings. Okay? I won't do it on a single chart map, because I set this up with an XY axis, and then that's how the map is defined. But if I don't like these coordinates and I want a different set, I just pick a different map, and then I can map from here to here. Okay? In fact, if we want to map from here straight to here, because that's really what a coordinate change is. A coordinate change doesn't really need this manifold nonsense on the middle. We just have a coordinate set, we want to transform to a new coordinate set. Then we can imagine that this thing is the map of phi 2 composed with the inverse of map phi 1. So we start with something here, we use the inverse of the phi 1 map. We use the inverse of this map to get to a point in here. And then we use the phi 2 map to get it to a point in here. Okay? So we might call this the phi 2, 1 map. Okay? But that's all the coordinate transformations. Yes?
Sorry, I'm a little unclear about this, but is this all in like this position dimension? Can you do like a time dimension?
Oh, no. So yeah, the manifold can be 4-dimensional.
Okay.
Okay? And we can map it to Rn, or we can map it to Minkowski space. It doesn't matter, but this space has got to be flat. This space can be curved. It can be time and space. Okay? It doesn't matter.
Okay.
All right? Okay, so now I'm going to make an observation with a bit of a payoff, which is going to be very, very important for us later on. But before I get to the importance of this, we're going to have to slug through some serious math. And again, it's going to involve lots of pictures with arrows. So I hope this is comfortable to you. Hope you all bought your quivers and your crossbows. We're going to have a ton of arrows to shoot today. All right, so I think I'm going to need this. I hope I'm not going to need this. I might need this. I'll just draw it again. So let's think about a coordinate change for a moment. So a coordinate change we can imagine as a set of functions of the old coordinates. Okay? And I know I'm going to, no, it's actually fine. Okay? So these are my new coordinates, and these are my old coordinates. All right? And now what I want to consider is the chain rule. Okay, this is a result from calculus which was invented by George P. Chain, who worked at the University of Idaho in the 60s. Okay, so what's funny, I told this joke in 2019. I'm going to tell it again, though I tell it every time. My partial differential equations professor at Georgia Tech, he said that shit to me. He said it to our whole class. I believed him. So I brought that shit up to my other professors and other students. They're like, yeah, George, hey, I know George P. Chain. They're like, what? What a moron. Anyway, George P. Chain invented the chain rule, and this is something that you should be familiar with from calculus. And I'm going to write it in a weird way at first, and then we'll settle into its application to coordinate changes. So if I have the derivative with respect to x of the function phi, which is a function of a function of x, which we'll just call g, okay? Another way to notate this is that this is d by dx of the map of phi composed g, okay? These just mean the same thing, all right? Then the chain rule says that in order to do this, we just say, okay, this is d phi dg dx, okay? And this is what I love about calculus. You know, if you squint your eyes and you just look at this and you say, oh, the dg's cancel. This is just d phi dx, which is what you were calculating here. Yeah, that's actually true. Now, it's not that simple, but it in many situations can come off that simple. Okay? All right, so this is the chain rule from calculus. But now what we're going to do is we're going to bump it up a bit. Oh, sorry, go ahead. If you're going to sit and ask a bunch of questions, you sit on that side of the room. No, because I rarely turn all the way around because I got to see them. If I can't see them, I just see their names. So hold on. Anyway, go ahead.
So I realize it's not relevant, but is there a place where I can find a quick explanation for like why those can't be treated as fractions? Because I've always been told that, but then every single time I'm told that it's in context of, but we're going to treat these like fractions.
Well, I'm about to show something that makes it not a fraction.
Okay.
I'm about to show you a not a counterexample, but a more complicated example where you can't treat it as a fraction.
Okay.
Okay? It'll help. It won't be a full explanation, but it should help a bit. So what we're going to do is we're going to bump this up, and instead of this being a single variable x and a single function g and a single function phi, what we're going to do is we're going to bump this to two functions of two variables, x and y. Okay? And we could go on to 3 and 4, but 2 is enough. Okay? And then, of course, we're still going to think of phi as a function of g1 and g2. Okay? So putting this into the same story, what I arrive at is the following. If I want to calculate the now partial derivative of phi with respect to x, partial because we have two independent variables, x and y, and I also want to calculate the partial of phi with respect to y, then we apply the chain rule, but realize that the chain rule now has to go through these two intermediate functions. So this is the way that it ends up looking. We have partial phi, partial g1, partial x, plus partial phi, partial g2, partial x, And then we have d phi partial g1 y plus partial phi partial g2 partial g2 dy. Okay? And this hopefully is where you see that you can't treat them as fractions, because if I could just cancel out this and make this d phi dy and cancel this and this, make this d phi dy, well that's 2 d phi dy, but this is d phi dy. So the multivariate example just eliminates that.
Okay.
Okay? All right. How are we doing? This hopefully should be relatively straightforward. Relatively kind of straight. Oh, okay, it's a little bit of a headache. I'm going to start asking some questions. Beginning with you. Let me think. If I wanted to, well, actually, I'll ask you a question on that. I'll ask you a question on that. Okay, so what I'm going to do is I now want to write this in index notation. That way, I can expand this to four intermediate functions, 4 independent variables. You know, we just go wherever. Okay, so I'm going to relate this in index notation. And so in index notation, this is going to say the partial with respect to x mu of phi, which is a function of g lambda, which is itself a function of x mu, is equal to the partial of phi with respect to g lambda times the partial of g lambda with respect to x mu. Okay? Now, these are not summed over. This is an argument of a function. Okay? So you can't sum over something which is exterior to the function to something interior to the function. So we don't sum over these, but I'm just showing you this. I could have just called this g lambda in MapLand. Okay? But I just want to show you what it's a function of. But at any rate, the reason why I say that, and by the way, this lambda is not actually sitting on this side either, because this is something that it's a function of. Okay? And the reason I say that is because the left-hand side of this only has one overall index. It's that mu right there. Okay? Well, the right-hand side of this only has one index as well. It's that mu right there. The lambdas are summed over. Okay? So if you take this and you write it out, you'll reproduce exactly this set of expressions. If you just let mu and lambda and everything take the values 1 and 2. Okay? Now, here's what we can do. We have a scalar function. This has no indices. It's a function of something which has an index, which is a function of the independent variables that also have an index. If this index takes the same values as this, I could relabel this. I could call this something a little bit different. I could call this g lambda prime of x mu. That's just relabeling the lambda as a prime. Okay? So I mean, I could just come in here and do this. Well, if I'm going to do that, then Andrew is going to tell me, what could I call the g there? G lambda prime, g lambda prime, x mu. What could I call that g? So remember, this is in order to incorporate this with the story that I was telling earlier, what could I call g? You want to phone a friend?
Yeah.
Okay. Anybody his friend? You have no friends. What could I call g?
What?
What could I call g?
I don't know.
I'm mouthing all of these words. I love you, Andrew. What can you call it?
X. Mu.
Nope, just
X.
x. Well, look, I mean, look.
Oh.
X lambda prime of x mu. What is that? That's a coordinate change. So if I just come in here and I replace all of the g's with x's, okay, what I've just discovered is the derivative of a scalar function of the old coordinates with respect to the new coordinates. Okay? Now, the scalar function phi is arbitrary. It's just a function I threw in there. I could put any function I want in there. So in reality, what we can do is we can just dump the scalar function phi. So just erase this and erase that. And just to make sure, because this is where it gets tricky, if I erase that phi, then this is not acting on anything. So you might think, oh, this acts on this. No, no, no. Okay? So what I'm going to do, for simplicity to make it clear, is I'm going to swap the order of these two terms, which doesn't change anything. We can always swap terms when we're doing index notation. So I'm going to swap the order of these, and then I'm going to drop the phi. Okay? Or if you prefer, we can get d by dx mu prime is dx mu prime d by dx mu. It doesn't matter either way. You can go from mu to mu prime or mu prime to mu. What did we just discover? Any takers? Or should I draw a card? Sean, what do you think I just discovered? You go from mu to mu prime. That's a
Coordinate.
And what did I just figure out how it changes?
Change the same way both.
No. What did I just discover the transformation law for? No, for this. What is this?
Is that a build-up?
No. I'm asking you, what is d by dx mu? Partial by partial x mu. It's a partial derivative. It's a partial derivative. No. I'm going to say this out loud, okay? I just found how the partial derivative operator transforms under a coordinate transformation, okay? So I can say that this is, whoops. The TLFPD. What do you think that is? Come on, guys, say it.
Transformation law for partial derivative.
Good. That's awesome. Okay, we're going to have some more of those in a few minutes. Okay? Now, do you remember the story we told in special relativity? In special relativity, what we said was, well, if I can figure out how a single thing transforms under Lorentz transformations, then I can take that single thing, I can demand invariance of other things, and I can use the one I know and the invariance to figure out how everything else transforms. So what was the single thing we started with in special relativity, where we knew how it transformed?
Vectors.
Well, they were actually the components of vectors, but what vector did we start with? So does everybody remember this vector? Oh, yeah, I guess we can do it this way. Where we said that the components of this vector are just coordinate differentials. But we know how coordinates transform, so we can figure out how these transform. If we know how t, x, y, and z transform, we automatically know how dt, dx, dy, dz transform. They transform the same way. Once we knew how this transformed, we said, this is invariant. This is a true vector. This shouldn't change if I change the descriptory language like coordinates. So if this changes in one way, this changes in the opposite way. So they cancel each other out. So that let us figure out how the basis vectors transform. Then we use this whole argument, well, if I got a basis vector and I got a dual basis vector, what is the other and they shit scalars? I mean, they poop scalars. Sorry, we didn't make this G. They poop scalars. And that let us take how this transforms and figure out how a dual basis vector transformed. But then we know that a dual vector has to be invariant. And if you know the basis transforms, you can say, well, the components of a dual vector inversely transform. So we figured out how everything transformed, starting with that single nugget. Okay? Well, we are now dealing with different transformations. We are now dealing with general coordinate transformations. So it's kind of hard to take something like this and figure out how it transforms. Now it turns out this is going to play a very important role in the transformation story, but we've got to bust through some math in order to discover it. Okay? So fasten your seatbelts. Grab your bows and, well, not your bows and arrows, just your bows, because I'm going to hand you plenty of arrows in this discussion. But this is going to get pretty ugly, I promise. But at the end, we'll get a result, and once we got the result, we're going to be able to take it and play out that same story we played out in special relativity. We'll figure out how everything transforms. Okay? So, this transformation story that I played out with the derivative was acting on a scalar phi. Okay? But one of the things you know about a scalar is that it has no coordinate dependence. So we might actually consider something slightly more complicated, like a vector. Now remember, vectors in special relativity are way easier than vectors in general relativity. General relativity involves curved spaces. Okay? So there's a whole set of ingredients that we have to add to the general relativity story that you don't see in the special relativity story, so let's add. Okay. Here we go. And man, I better draw this at the right place because otherwise I won't be able to add to it. So let's take our manifold M. And let's consider a point in the manifold which I shall call P. Okay? And then what we're going to consider is a path through the manifold which passes through the point P. And this path is going to be accompanied by a map we call gamma. Okay? And what we have is that gamma, well, hold on, let me first draw what I'm going to map into that curve. So first of all, I'm going to take a set of parameters which I call lambda, which exist on the real line, R1, okay? And a particular value of those parameters might be something that I call lambda p. And then there exists a map, and it's just a map gamma, which takes me from a point on this line lambda into the manifold, okay? So this is a map from R1 into the manifold. Okay? Now, I want to be really cautious. This map from the real line into the manifold only returns points along this particular curve gamma. It can't give you the results of any other points in the manifold. It's just defined by a curve in the manifold, a one-dimensional curve. Okay, a one-dimensional curve mapped from a one-dimensional line. That makes sense? Okay? Is this a chart? Why not? Okay? Manifold, map to R, Exactly. No, it's not a chart, because this can be an n-dimensional manifold. This is R1. So don't think this is a chart. Okay? Now, what we can do is we can add in a second map to R1. And in this case, we'll call the parametrization of this line by alpha. Okay? And what we can do is we can define a map from the point in the space to the point alpha prime, where this is a function f, and f, which is a function of p, and in this case I'm just going to call the result of the function of f acting on the point p, alpha p. The function p, or the function of points in the manifold, is a function from the manifold into R1. Okay? So whereas gamma took me from R1 into the manifold, going this way, f takes me from the manifold into R1. Okay, now notice, this map is associated with the curve gamma, because it's only quantified by a single number. Okay? However, the function f is good over the entire manifold. Okay? All right? Now, useful for any point on the manifold. And now what we can say is, okay, what about mapping straight from here to here? What does that look like? Well, as we talked about before, this is the map of f composed with gamma, where remember when I have a chain of maps, I act with the rightmost one first, and then I act with the ones to the left of it. So this is doing the gamma map first, so starting with the point lambda p, gammatizing it. I'm smiling, you're not. Gammatizing it to the point p, and then effing it. You know, when I taught this class in 2019, they laughed so much harder than you guys are laughing at these same damn jokes. Anyway, it doesn't matter. They effed it to the point alpha p. So this guy is a map from where to where? Gus? Are you in the room, Gus? Gus? Yeah, R1 to R1. This is a map from R1 to R1. Thank you. All right? Okay. Another way to annotate this is to say that this is f compose gamma, where if I take the point lambda p, it gives me back the point alpha p. So this is a specific example. If I take lambda p, it gives me alpha p. But I can generally map any point on this line to points on this line. Okay? Now it gets interesting. Are you ready? Yeah.
So is f a chart from lambda to alpha?
No, it's not a chart. Because again, this is an n-dimensional manifold. And I might write it up here. And this is one-dimensional. The charts always have to map from the dimensionality of the space, of the manifold, into a copy of Rn, where the degree, or the dimension of the n there is the same as the dimension of the manifold. Okay? So I'm not dealing with charts at all. I will in a minute. Okay? Now here we go. Are you ready? This is a single chart. I'm sorry, single chart, a single curve. Sorry, it's a single curve. We can do better than that. We could consider the point P, and we could consider the curve gamma, but we could also consider the curve beta, and we could consider the curve psi, and consider the curve delta, okay? Each of these curves would be parametrized by different symbols. So maybe I've got lambda is the parameter of the gamma curve, and then I can do, I don't know, I might, I could do the alpha, no, the alpha's over there. Oh, shoot. Anyway, I don't know why I parameterized gamma by lambda, but now I don't know what to parameterize psi by, delta, beta, or p. But anyway, you can parameterize each of them by some symbol, okay? All right? Again, the curve is gamma. This is the parameterization that you're using to move along the curve gamma, okay? And, well, actually, I got to write it down. So I'll say, hold on. I will say, okay, here we go. Let's do this. Let's call this capital psi, and oh shit, what's the capital delta look like? Is it just a really big triangle?
That's the triangle.
Oh, sorry, it's the triangle like this or the triangle like this? That one?
No.
That's the other one. I thought it was the other one.
Upside down is del.
Yeah, well, del. Yeah. Okay. Yeah. Anyway, it doesn't matter.
Theta?
I mean, I could call this theta like that. Anyway, and unfortunately this has got lambda. So, but anyway, I can do like little psi, little delta, little theta. Anyway, it doesn't matter. Okay, so now you know which curve the parameter is associated with, hopefully. Okay. All right. Now, here's what's really interesting. If I consider, oh no, sorry, I'm getting ahead of myself in the story. There's a very important piece to this which I have to tell, which I haven't told. So forget about this for a moment, blank on that. I'll come back to that in a second. It's fine. Okay, sorry, I forgot this. All right, so here's an important observation, folks. If I change the value of lambda, what happens to the value of alpha? It changes, okay? So if I'm changing alpha at a rate, should there be an associated rate of change of alpha? Yes, okay? So what we could consider is df d lambda, which I can imagine is d by d lambda of the composition map of f composed with gamma. Okay? Now this has a very specific name. This is called the directional derivative of f composed gamma along gamma. Okay? All right? Now, I want you to notice something. In this entire story, I've just given you a derivative, okay? It's a directional derivative. Never at any point have I mentioned coordinates. Coordinates, they're just like a way to describe things explicitly, but we don't need them to define a lot of stuff, okay? But we'll do that in a minute. Now, let's come back to the story, okay? Now, I can imagine that all of these different curves, parametrized by all of these different variables, all of which live in R1, can be thought of as a set of derivatives, okay? So I can imagine that from this set of curves, I'm going to get a set of derivatives. Okay? Where each derivative just corresponds to the derivative along a different path. And again, this is not the only path. I can choose any path that I want. So just imagine the board gets dense with these paths. Okay? Now here's the interesting observation. This set of derivatives forms a vector space. Does anybody remember what it means to define a vector space? Or what is a vector space? I'll give you a couple of rules that vector spaces have to satisfy. A, if I take two vectors and I add them together, I have to get another vector. This is closure under vector addition. B, if I take a scalar and I multiply it by the vector, I need to get another vector. That's scalar multiplication. That's closure under scalar multiplication. If I take a vector and I multiply it by a scalar, I get another vector. If I take two vectors and add them together, I get another vector. Those are closures. Okay? We have associativity. Of the addition of vectors. We have the commutativity of the addition of vectors. We have an identity in the addition of vectors. What's the identity in the addition of vectors?
Zero vector.
The zero vector, exactamundo. We have inverses in the vector addition. And then we have other properties which are rules for the scalar multiples. Okay? It might not be obvious, but this set of derivatives actually satisfies all of these requirements. Okay? So these things, these directional derivative things, form a vector space. Oh, wait a minute. Hold on. Are these defined all over the manifold?
They're only defined at one point.
They're only defined at the point P. These curves moving throughout, okay, this definition is only at the intersection of all of them through the point P. So we've just defined a vector space at the point P. What would you call it? What would you call a vector space? Ooh, Sam. If I pick a point on a manifold and I define a vector space from derivatives along the various paths that go through that point, what's it's the tangent space. Exactly. This is our definition of the tangent space at the point P. Okay? Why do I care about tangent space? What lives in tangent space? Vectors. We didn't even have to talk about tangent space when we defined vectors in special relativity, but I told you the tangent space would play a very important role in general relativity, largely because of the fact it's forced on us that if we're in a curved geometry and I consider the tangent space at one point, it can be radically different than the tangent space at another point. If your space is flat, then most often you can just define one tangent space that's global everywhere, and then have all of your tangent spaces aligned. You don't have to, but you can. Okay? So we now have a working definition of the tangent space at a point P in the manifold. And of course you could go through this construction for every different point in the manifold. We won't need to do that, but that's in principle how you could build up all of the tangent spaces in the manifold. Now, we have tangent spaces, which we know are where vectors live, but I'd really like to add coordinates to this story, wouldn't you? I mean, who likes these abstract mathematical maps? Arrows. From here to here, from here to here, boom, boom. We want to do this with coordinates. We like to write equations with coordinates. Well, Shaylee, if we're going to need coordinates in order to, well, actually, if we want to introduce coordinates to this story, which has been developed without them, what aspect of manifolds do you think we're going to have to rely on? Well, what are the properties of manifolds? They're n-dimensional. When we define a manifold, what's that definition use? Yeah, no, that's fine, definitely. Yeah, which is composed of what? That's fine. Well, no, so the Maximal atlas, we take this and we cover it with a lot of what? Charts. Each chart comes with a map to Rn. And Rn is where we can define coordinates. So if we want to introduce coordinates to this story, we need to introduce legitimate charts into this story. And I want to remind you, these maps are not charts. Okay? So here we go. Let's introduce a chart to this story. And, oh boy, I can do this. I think I can do this. I think I can do this. Yes, I can do this. Okay, so I'm going to have a map into Rn, where n is the same as the dimensionality of the manifold. I'm going to associate with this chart a coordinate system. And then I remember that any chart comes with a map from any point in the manifold, and I can pick the point P into points in the copy of Rn. And this map might be called phi, which again takes arguments as points in the manifold, and it maps us from the manifold to Rn. So if I feed the map phi, a point in the manifold, I get back a point in Rn. In particular, if I give it the point P, I'll get the associated point in Rn. Okay? Now, hold on. I can do an inverse. I can take this point and map it right back to the point P using the inverse map. But the inverse map is not going to act on P, but rather it's going to act on a point in this space, which I can describe by the coordinates x mu. So this is going to take me from Rn to the manifold. Okay? Now you might object, because I said to you that the charts must have an image which is open in Rn, and the map must be injective, 1-to-1 and on-to. Okay? No, sorry, it's not on-to, it's just 1-to-1. But I also said that given the lack of the bijectiveness, I can't define an inverse. So why am I defining an inverse? Yes?
Is it because that's the space, not necessarily the specific point?
That's the space and not necessarily the specific
He said
point.
this acts on the space, or x mu is the space that we're talking about instead of we're
Okay, so if I'm just talking about the point P and its corresponding point here, which I could call this, like x of P, y of P, etc., then yes, the inverse of that map is well defined. Okay? But can I broaden the definition of that inverse?
Does it count as a chart if you just map everything in the manifold to 0? To 0 in R.
Right?
Yeah, that's not one-to-one.
That'd be zero.
Well, every one in M corresponds to a point in.
But it has to be a one-to-one map. You've got to have a different image for each point in the manifold that you're mapping to the
I
Rn.
see.
Yeah.
And wouldn't that be zero dimensional?
Can you map from Rn to the tangent spaces using that inverse?
Okay, that's an interesting question. Can I map from Rn? Well, actually, I don't want to map to the tangent spaces. I'm just asking, can I map from Rn back to Mn? Can I do that? That's what the inverse does. Can I map from Rn back to Mn? Who says yes? Who says no? I say no. So here's the thing. If I take the entirety of this manifold, whatever it is, let's just say it's not infinite, and I map it through a chart to points in Rn, it might not cover all of Rn. It might just I'm just going to draw a manifold with a boundary because it's hard not to. If I took a circle and I mapped it into Rn, it might form a circle. Well, there's points in Rn which are not part of the circle. This is why the map is not onto. It doesn't cover every point where it's going. So it's not invertible. I can't tell you the inverse of this point because it's not even in the image. Okay. However, if I restrict myself to only the image, then I can make an inverse. Because then it's a bijective map. Because I'm mapping one-to-one from here to here, and everything in the image is accounted for through the map. Okay? So even though we can't in general define an inverse, if we're just thinking about the image of the map, then we can define an inverse on those. Does that make sense? Don't worry, that's not a super important detail. I'm just going to use that inverse. Okay. So here we go. Let's get rid of this. All right, let's bust through this. Okay. Now, what I want to do is I want to mature this map into the following form. Now, I would like to introduce F compose gamma in terms of F compose phi inverse compose phi compose gamma, which is again something from lambda to alpha. And if I'm acting on a particular point, it's lambda p to alpha p. Okay? Now again, let's follow this map, just in terms of the pictures. Remember, I act with whatever's to the right first. So I start with a point lambda p. I gammatize it. Boom, it gets me to the point P in the manifold. Then I phi map that, or I phi it, to this point here in Euclidean space. And then I phi inverse it back to the point P. And then I F it to the point alpha P. Okay? That's what this sequence is doing. It's mapping me overall from lambda P, alpha to alpha P. Golly, I gotta get in front of the board and write it correctly. Okay? So really this chart step is just, it's kind of inserted as sort of the identity, in a sense. Okay? Now, what one can imagine that this sequence of maps is taking the point lambda p, and I'm just going to say what I just pointed out in the picture. It gives me back the point p that's in the manifold under the map gamma, and then I map that with phi, and it gives me the coordinates associated with the point p in this in this passive Euclidean space, so that's an x mu. And then I phi inverse that back to the point P, and finally map it with F to the point alpha P. Okay? So that's another way of symbolizing this chain of maps. Are you ready? It's going to get a little bit ugly, but the end is going to be wonderful. Let's go back to our consideration of how changing this changes this. Okay? Where this time we're going to have the phi and the phi inverse map as part of the story. So here we go. I can say that this is the derivative with respect to lambda of f compose phi inverse compose phi compose gamma. Okay? Now, this map right here, phi compose gamma, is a map from R1 to Rn. Okay? Remember, I start with a point in R1. The gamma map takes me to the point P, and then the phi map takes me here. This is an element of R1, this is an element of Rn. Okay? So this is going to have n components. This doesn't have any components, but this is going to have n components. So one way that we might write this, oh my God, yes, okay? One way that we might label this is as phi compose gamma mu. Because after all, the result of mapping from here to here to here is going to leave me with something which has components. So I might as well just put a little index on there to say this is going to have components. Okay? All right. Now here we go. This, I can use the chain rule to establish that this is partial of f compose gamma inverse, partial phi compose gamma mu, d phi compose gamma mu, d lambda. Okay? This is using the chain rule. For the function f compose gamma inverse being a function of phi compose gamma. Okay? That's just saying that the result of phi compose gamma here are the points here. So I can take those and I can feed them into this sequence of maps. Okay, if I want the derivative with respect to lambda, I can just apply the chain rule to this set of nested maps. Okay? Now, are you ready? Since phi compose gamma mu is a map from R to Rn, we might as well call it x mu of lambda. Why not? This is just saying, if I take a point lambda and I feed it to the map phi gamma, boom, boom, I'm going to get back a set of coordinates, x mu. So why don't I just write it as x mu as a function of lambda? Does that make sense? Okay? Since f compose phi inverse is a map from Rn to R, because again, that map is going to go from here, that's the phi inverse part, and then the f part. So it's f compose phi inverse. That's starting with a point in Rn and giving me back a point in R. Okay? We can call this f of x mu. Right? Well, putting in these notations into here, we can now write df d lambda is equal to df, partial f partial x mu dx mu d lambda. Okay? All I did was I took x mu and plugged it in under where I see phi composed gamma, and I took f of x mu and plugged it in under where I see f composed gamma inverse. That's all I did. Yes?
Okay, so on the line that says use entangle over block, why is it f composed with gamma inverse and not phi inverse?
Oh, yeah, it is. It is phi inverse. I have it written wrong in my notes. Sorry. Yeah, it should be phi inverse. My bad.
Okay, and
But
then
that's
it's also
it's-
slightly over on the left on that same line. You have gamma inverse again.
Yeah, sorry, this should be fine. My bad. Thank you. Okay? Now, you ready for the good news? F is arbitrary. Who cares about F? So what I can say is that d by d lambda, and again, I'm going to do the same switcheroo, make sure that I don't apply the empty derivative here to this, is dx mu d lambda partial x mu. Okay? This is any directional derivative in the tangent space. Oh, I erased it. Remember I had this set of directional derivatives? Okay? This, I can imagine, are the components. Remember, this is a directional derivative in tangent space. It is part of a vector space. These are the components of the vector. What then are these?
Basis.
It's a basis. Okay. So what we have established through this line of reasoning is what is called a coordinate adapted basis in tangent space. Look, tangent space is a vector space. That's well defined before you put any coordinates on it. Okay? So, I can, vectors exist without the use of coordinates. But then I can throw down a set of coordinates, and then the vector can be written in terms of its components and the basis, but that's all defined with respect to the coordinate system you chose if you're using a coordinate adapted basis. There are other bases, but these are the most simple ones. Okay? So we had to add in this coordinate part of the story in order to get a basis for the tangent space. Before we added this in, we had defined tangent space. We knew it was a vector space, but we didn't have a basis to use. Here we're introducing coordinates and therefore a coordinate basis. Okay? Wait a minute. This is a vector. These are the components. These are the basis vectors. What would an arbitrary vector look like? It will have components multiplied by the basis vectors. Remember, this is the same as d by dx mu. Why is this important? Go ahead.
It says that vectors will change with the space.
Vectors will change, well, actually, a vector itself won't change with the space. A vector exists regardless of the coordinates.
The components will change.
The components will change. Will the the basis vectors change?
Yes.
How will they change?
No, they will, but the components will change.
No, the basis will change. How will it change?
It has to be inversely to the change of the components, but
It does. But can anybody tell me explicitly how the how the basis vectors change? This is the transformation law for a partial derivative. What are the basis vectors? They're partial derivatives. This is the nugget, which is going to seed the rest of our discussion, which will go very similar to special relativity. We know how one important ingredient in the transformation story transforms. We know how the basis vectors transform. This is not like we did in special relativity, where we said we know how the components of a particular vector transform. Here we actually figured out how the basis vectors transform. But a vector should not transform. So if these transform one way, these should transform in the opposite way. So what we can say is, make some room, V mu goes to V mu prime, V mu partial mu equals V mu prime partial mu prime. That's the total vector. The total vector doesn't care what coordinate system you use. Okay? Well, I can write this as V mu prime times the transformed version of this, which is just this right here. So I can write dx mu, dx mu prime, partial mu. And then what I can say is, well, if V mu prime transforms in this manner, where this thing is just delta nu mu, then obviously this expression is going to reduce to this expression. So if d mu transforms with this factor, the components transform with the inverse of that factor. Because this is a matrix, this is the inverse matrix. They're multiplying together to basically give me the identity. Okay? Okay, so we can add to our list of successful things the idea that V mu prime is dx mu prime dx mu v mu, and we could call that the transformation law for vector components. And we might as well call this the transformation law for basis vectors. Okay? Now you all know where this goes next. I now know how the components of a vector and the basis vectors transform under an arbitrary coordinate transformation. What do you think I do next? Drew. Say it again?
Are you asking for Marina?
Yes.
Okay. Repeat the question.
We now know how the basis vectors transform and how the components of vectors transform. Where do you think we take the story next?
Do tensors or just
Well, before tensors in general.
dual vectors?
Yes, we should translate this to dual vectors, okay? And what's interesting is the story for dual vectors plays out exactly like it did in special relativity. Okay, so I'll just go through this quickly. Now that we know how the basis vectors transform, we can say, okay, a dual vector has components given with a lower subscript times the basis dual vectors. But remember that a basis dual vector eats a vector and poops out this scalar. And remember, we've identified in this case that these are just d nu, partial derivatives. So we can call these dx mu. Okay? Then what we have is that dx mu, partial nu, this is a basis dual vector eating a basis vector, should give me the same thing. Sorry, yeah, it's fine. If I transform the coordinates. But this tells me that the basis dual vector should transform as follows. Dx mu prime, dx mu, dx mu. That is, the basis dual vectors should transform exactly like vector components. Well, now what do you think the components of a dual vector should transform like? The basis vectors, okay? So then we can say that omega mu goes to omega mu prime, which is partial x mu prime, omega mu. Transformation law for dual basis vectors. Transformation law for dual vector components. Well, folks, do you think tensors are hard? No, we know how to extend this to tensors. If I'm given a tensor and I want to transform it, first of all, I transform every index. Okay, I don't transform some of them and not others. I transform every index. And if it's an upper index, it gets a transformation factor associated with a vector index. And if it is a lower index, it gets a transformation factor associated with a dual vector component. Okay? So in the end, this is going to be D, 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 T, mu, nu, alpha, beta. And then all we do is fill in everything. I need to take the mu, I need to eliminate it by summing over a mu and replace it with a mu prime, so I can just do that. I do the same thing with the nu. With the alpha, I want to sum it over something and replace it with alpha prime, and the same with beta. Okay? That's the transformation law for tensor components. Okay? Are there any questions? Now, hold on, I'm going to very quickly run you. No, actually, we'll just start with this next time. I'm not going to do it. Okay? So we'll start next time with a discussion of the difference between this and special relativity. There is a very, very key, very, very important distinction between this story and special relativity and this case of general relativity, which is actually going to be a huge bump in the road for us. Turn it off. Thank you.